Hello everybody, welcome to another video lesson. Today we are combining two of your favorite topics. We're going to combine your conic sections knowledge with polar coordinates and polar equations. Okay, we're looking at polar forms of conic sections. So at the end of this video, we will be able to identify, write, and graph polar equations of our conic sections. Okay, before we get started, I do have a book recommendation for you. It is called SPQR. It is a fantastic account of the history of ancient Rome. If you're one of those kids who thinks history is super boring, like I used to be, this is a very good book, even if you feel that way. So I would encourage you to check it out. Okay, but now let's go ahead and get into our concepts with our polar equations. Okay, looking at our conic sections here, I've got a parabola, an ellipse, and a hyperbola. Now we are not looking at any degenerate conic equations, okay, no lines, no points, and we're not looking at circles either. So we're just looking at these three conics within the context of our polar equation. Now, regularly with our rectangular conics, we remember that E is the ratio of C and A, right? However, for our polar equations, we also have a different definition for E, and we call this the focus directrix definition. Okay, this value here, E, is actually also known as the ratio, not only between C and A, but also between any point here. If I were to pick a point, you guys know that any point on, say, a parabola, right? Any point that I pick, that distance from the focus to that point is the same distance as that point to your directrix. So that is why for a parabola, the E value that we get is 1, right? Because this ratio here is the same. PF is equal to PD if I take a look at this distance and this distance. Now, I didn't write these to scale, so my apologies. So you can't really see that very clearly, but we know mathematically that that is correct. Okay. Now, for an ellipse, we also have a directrix, and similarly, we have a ratio for the distance between P and your focus and P and your directrix. And lastly, again, for our hyperbola, P to F, that distance has a certain ratio with P to D. Now we know that for an ellipse, our E value is in between 0 and 1. We said for a parabola it was exactly 1, and for a hyperbola we know E is greater than 1, which means that the distance from P to F for a hyperbola is greater than the distance from P to the directrix. And likewise, from P to F for an ellipse, that's going to be less than the distance from P to D from P to the directrix for an ellipse. So with that in mind, we're going to go ahead and derive a polar equation for a conic section here, and we are going to do this in this class only in the context of having the focus on the origin. Okay, so our focus is always going to be on the origin in this case. So here I've got an upward facing parabola with the focus on the origin, or the pole, as you might think of it as well, in terms of our polar equations. So I've got my focus here, we've got our curve, which means, since this is an upward facing parabola, that means my directrix has to be below it, right? Which means the directrix has to be a horizontal line. That's going to be y is equal to negative d, we're going to call that, okay? So if I pick a point here, this point P has coordinates x, y, and then D here, this distance between P and D, well, that's just the distance D, right, with y is equal to negative D. That is equal to that distance, horizontal distance, plus whatever y is, right? So this distance is y plus d. Okay, so if I start with my focus directrix definition for E, we can go ahead and start deriving this. So I will go ahead and solve for PF. So PF is equal to EPD. Now I can think, okay, what is this distance PF? Well, if I use my Pythagorean theorem, I know that that is going to be the square root of x squared plus y squared, right? And then I'm going to substitute PD because that is just the distance y plus d like we have right here. And now we can start substituting in some of our polar terms, right? So I know that the square root of x squared plus y squared, well, that's just equal to r. And then anytime I see a y for a polar equation, I know I can substitute in r sine theta. So let's go ahead and substitute those in. And then I'm going to distribute this e here, distribute that. So it's going to be r is equal to er sine theta plus ed. Now I'll go ahead and subtract er sine theta on each side, and we'll factor out my r, and then we'll divide by our 1 minus e sine theta, okay? And what we're left with here is the polar form for this conic section, okay? So this is one way to derive this, and there are actually 4 different iterations or 4 different variations of this exact polar form here. Okay, so let's take a look at that. So they're all very similar here. I've got ed over 1 plus e cosine theta, and then ed over 1 minus e cosine theta, and then I've got plus e sine theta and minus e sine theta as well. Okay, so all of these are going to tell me, and I have parabolas up here, but this is just to show the orientation of all of my conics within these with these given equations. Okay, so this would be the graph for that one, and then if I kind of scooch along here, that's the graph for minus e cosine theta, and then plus e sine theta, and then this is the graph for minus e sine theta. Okay, so we can think of it in a couple different ways here. So anytime we have a cosine, okay, cosine is always our x value, right? So we can think of this as whenever we have a horizontal conic, that's going to have the cosine in there, all right? That's going to have the cosine. So whenever we have then the plus or minus, how do we differentiate between that? Think about where my directrix is, okay? If I have a plus e cosine theta, then my directrix is going to be some positive value. E is equal to positive d. It's going to be on the right-hand side of my focus, okay, or the pole. Okay, and then if I have 1 minus e cosine theta, my directrix, which will be x equals negative d, that's going to be on the left-hand side, right? The negative side of the pole. So I got minus, and I have a negative directrix. Okay, so all these red dotted lines are my directrix. And then likewise, so if I have sine theta in my function, then I'm going to have an upward or downward facing conic. Okay, and then if I have plus e sine theta, then I'm going to have a directrix that is above plus, okay, above the pole, and minus sine theta, y is equal to negative d. So that's going to have a directrix that is below the pole. Okay, it's going to be below the pole. So minus, I'm going down, plus, I'm going up. Okay, and same thing here, plus I'm going to the right, and minus I'm going to the left with my directrix. So that's a way that we can kind of familiarize ourselves with these general forms of our conics in polar form. Okay, so that's our one concept, guys. Let's get right into some examples. All right, example 1, we're going to identify conics from their polar equations. Okay, we need to determine the eccentricity, type of conic, and equation of the directrix. Okay, equation of the directrix is the third thing we need for each polar equation. Okay, so first thing we need to do here, we need to get this equation in our general form, right? So r equals ed over 1 minus e cosine theta. And I'm saying this needs to be 1 minus because I have minus here. Okay, so this is a difference on the bottom. So I just need to get this to flip sides. Now, how do I get this to flip signs? Well, we need to factor out a negative 1. So if I factor a negative 1 out here, and then my negative would cancel with the negative 6 on the top. So I have 6 over 1 minus 3 cosine theta. So right away from here, I can tell that e is equal to 3. Okay, whatever this coefficient is right here is my e value. Okay, so e is going to be greater than 1, so I know that I have a hyperbola. Okay, and then we can go ahead and set ed. Taking a look at my original equation, we're going to set ed equal to negative 6. Okay, so negative 6, I will look at and say, I'm going to substitute 3 in for d. Okay, and then I get d is equal to negative 2. Okay, so does that mean that my directrix is x equals negative 2 or y equals negative 2? How do I know? Well, taking a look at our general form here, I can see that this is a sideways facing, because I have cosine, so it's sideways facing conic section, so it'll be a hyperbola. which means that I will have a directrix on the, if this is my pole here, okay, my directrix is going to be on the left side of the pole. So it's going to be negative. And then what is a vertical line? Well, a vertical line is x equals something, right? Okay, so since that is a vertical line, I know that my directrix will be x equals -2, and we have a hyperbola with an e value of 3. So that's how you do a problem like that. Go ahead and pause the video then, and you guys try to do the same thing, identify eccentricity, type of conic, and the equation of the directrix for this polar equation here. All right, here's what I got. An ellipse with an e value of 0.2, a directrix equation of x equals 5/6. Alrighty, now we're going to look at writing conic polar equations. We're going to write and graph a polar equation and directrix for the conic with the given characteristics. Okay, so I know that E is 1, so I know right away that we have a parabola, and I have a directrix of x equals 2. So I know that my D value is 2. So D is 2 and E is 1. Then I know ED, which is the numerator of my equation, right? That's just going to be 1 times 2, which is 2. So now we have a vertical line that's on the right-hand side of the pole, right? So I know right away, kind of start to sketch this and see what this looks like. It's going to look something like this, right? It's going to be opening to the left because my directrix is on the right-hand side, okay? And again, the focus is always on the pole in these equations or in these contexts, in the context of this class that we're going to look at this, okay? So now I can see that my general form is going to look like ED over 1 plus cosine theta. So I know what ED is, so let's just substitute that in, and I get R is equal to 2 over 1 plus cosine theta. Again, my E is 1, so that could be like 1 cosine theta here, which we can just write as cosine theta. All right? And then I'm not going to go through the process of graphing just for time's sake, but our parabola will look something like this. All right, so you guys pause the video and see if you can write and graph a polar equation and the directrix for the conic here with these given characteristics. Okay, here's what I got. Here's the work here on the right and the graph on the left. All right, let's take a look at our third example here. We're going to write the polar equation in rectangular form. So we're going to convert this from polar to rectangular, okay? So we have the general form equation here. We're working with R equals ED over 1 minus E cosine theta, okay? So I should know right away kind of what this looks like, at least the orientation of our conic. Let's go ahead and look at our E value. Well, we know our E is going to be 0.8, which is less than 1, so we know that is an ellipse, right? So I know my directrix then, since this is, it's going to have a directrix that is on the left-hand side of the pole, right? So I know I'm going to have a directrix of x equals negative something. How do I find that negative something? Well, we know E, and we know what E times D is. Okay, we know ED is 1.8, so let's go ahead and substitute E in there and solve for D. We get 2.25, so we have a directrix of x equals negative 2.25. Okay, so with that, we can start to really kind of sketch this, and we can see, since we're working with an ellipse here, one of our foci is on the pole, and I know that my vertices are going to be at what angles? Well, they're going to be at theta equals 0 and pi, right? So let's go ahead and start plugging in 0 and pi here. So R is equal to 1.8 over 1 minus 0.8 cosine of 0. So that's going to be 1.8 over 0.2 or 9, okay? So the polar coordinates here are going to be 9, 0, okay? Which we need to think now, how does that correlate to the rectangular components? Okay, well, 9, 0 is actually the same in rectangular, right? It's going to be 9 along the horizontal axis, and we're not going at any angle, so it's just going to be sitting there on the horizontal axis, right here, right where we have this point right here, okay? So again, let's go ahead and plug in pi. When we plug in pi, I get 1.8 over 1.8, so that's 1. Okay, so the polar coordinate there is 1 pi. Okay, 1 pi, however, corresponds to a rectangular component of, or a rectangular coordinate of -1, 0, okay? So hopefully you guys can imagine we're going around, okay, pi, or 180 degrees, right? And then we go out 1, okay? So when I think of that as an xy plane here, we can think of this as going over 1, and we're not going up or down at all. So that would be -1, 0. Okay, so my vertices are going to be at -1, 0, and 9, 0, okay? So I can tell now what my center is, right? My center is in the midpoint of these, so it's going to be at 4, 0, which automatically tells me my h and my k value, which is very nice. We're halfway there. Only thing we need now to put this into rectangular form is going to be the values of a and b. So what are those values? Well, from the center to my vertex is a, right? So from the center to vertex is a, so I know a squared is going to be 25 because a from 4 to 9 is going to be 5, okay? So then we need to figure out what c is, right? So my c is the distance from my focus to my center, okay? From focus to center, that is c, right? So I know my focus is at the pole, which is at 0, 0. I know c is at 4, 0. So I know that my distance c is going to be 4, okay? And the relationship for our ellipses are going to be c squared equals a squared minus b squared, right? So solving for b squared and plugging in our 25 and 16 for c squared and a squared, that gives me a b squared of 9. So I can just plug in my hk, a squared, and b squared, and I get this rectangular equation right here. Okay, last example here. You guys pause the video and see if you can convert r equals 5 over 1 plus sine theta into rectangular form. Pause the video, see what you get. Alrighty, here's what I got. I got x squared is equal to -10y minus 2.5. Okay, this is my work, so hopefully you got the same thing. If not, check it out though. But that is it for this video, guys. So good luck with your practice.